Hi, I'm Christiana, and I'm going to present our paper entitled Evaluating Local Intrusion Detection in the Internet of Things, a work implemented by myself and Dr. Vasos Vassiliou. The Internet of Things is a network of smart, diversified devices that allow the creation of various new applications. And as with any other network, security breaches are an imminent threat. If a smart device within the network is compromised, it may result in inaccurate and misleading information. Security measures have been proposed and adapted to ensure confidentiality, data integrity, authorization, and data availability, but require memory and CPU power that may not be available at the edge nodes of the IoT network. There is also the risk of potentially new forms of attacks that the security mechanisms fail to prevent them from penetrating the IoT. These attacks need to be identified and tackled with as early as possible to avoid the widespread of falsified data or denial of them. And this is the general motivation of the intrusion detection systems, which is to detect the presence of unauthorized intervention within the network before they cause irreversible or any damage at all. There are two main detection methods. One method is to search for the specific patterns of previously seen attacks, and the other is to detect abnormal behavior. In this work, we focus on the anomaly detection to detect known but also new forms of attacks. Anomaly detector is classified based on the method of profiling normal behavior and detecting abnormalities. We propose binary logistic regression as a technique that can be installed on the IoT nodes, monitor their local activity, and detect abnormalities. The evaluated technique is part of a lightweight IDS called MITS. The results in this work are presented using multiple binary classification metrics and explore the BLR model's precision and sensitivity, along with the accuracy and the quality of the binary classification. To construct the BLR models and to evaluate them, we took the following steps. First, monitor and gather local node activity in benign and malicious scenarios in two different network topologies and with 4 different attacks. Second, define local node activity using the BLR. And third, to implement and evaluate MITS. Two types of attacks are used, the selective forward and the black hole. In selective forward, the malicious node selectively chooses which packet to forward and which to drop. It was implemented with 2 versions, the forward duration and the block node. The forward duration is set such as each packet has a 50% chance to be forwarded, otherwise it drops. The block node attack targets specific neighbors node's packet to block. The selection of the node to be blocked is done randomly and changes during runtime. A compromised node under the influence of a black hole attack lures traffic towards it by advertising that is one hop away from the gateway node. It was used to complement the selective forward attack to attract more traffic towards the compromised node and then selectively drop packets, thus affecting a wider range of nodes in the network. To collect the necessary network activity needed to define and evaluate the detection capability, we made use of RMT, a runtime monitoring tool, which is part of MITS. It monitors local node routing information. During the offline training stage, RMT provides routing layer data to define normal behavior. To retrieve data from both benign and malicious local activity, we define 2 types of scenarios, the benign and the malicious scenario. In a benign scenario, all nodes within the network are executing a benign application. In the malicious scenario, one node within the network is executing a malicious application. The topology we use for defining local node activity places the sink in the middle and is directly connected to other 4 nodes. The scenarios were evaluated in 15-minute experimental time, The nodes were allowed a 2-minute period to connect to the network and then start sending packets. RMT provided writing layer data at one-time intervals. The BLR statistical tool is used to derive the detection models. It is used to predict a binary dependent variable. In this case, the dependent variable is whether the node activity is caused by a compromised node or not. Preliminary results have shown that proper training of the BLR models for the IoT platform had to be generated, as the existing BLR models derived by simulations failed to detect the malicious nodes. 4 metrics were used to evaluate the detection model results. The accuracy, which shows the ratio of correct classifications of the input activity to either benign or malicious over the total local node activity used for the specific experiments. Recall shows the ratio of true positives, the alarms that were raised by the malicious node, over the total alarms raised. Precision shows the percentage of correctly identified malicious nodes within the network. The MCC, the Matthew Correlation Coefficient, measures the quality of the activity classification. The MCC normalizes the sizes of benign and malicious activity present to avoid unequal classification rates. 2 topologies were used for evaluating means in the simulator and the IoT platform. The sink in the middle topology was used for defining node activity, and it was also used for evaluation. The BLR models were also evaluated using an unknown network topology, in which no prior training was performed. The new network topology places the sink at the top left corner of the grid and has 2 nodes directly connected to the sink. Now, in the training stage, the BLR, the dependent variable, had 2 values, 0 for benign and 1 for malicious. At the evaluation stage, the BLR takes as input local node activity from the RMT and outputs a value between 0 and 1, the dependent variable. A decision threshold is set up to round the value to either 0, classifying the incoming activity as benign activity, or 1 for malicious activity. The decision threshold determines the security sensitivity of the IDS. As with a low decision threshold, there are more false alarms, but more possibilities to detect the malicious node, while setting up a high decision threshold, there are less false alarms, but with the risk of not detecting malicious nodes. The current slide presents our results when we evaluated the BLR detection model in the simulator. The left table shows the evaluation results of the network topology used to train the BLR models, the sink in the middle topology. The selective forward-forward duration achieved the highest values on the performance matrix when the decision threshold was more than 0.9, whereas the rest of the attacks achieved the same performance values when the decision threshold was 0.5. Now, the MCC shows that the BLR models were highly correlated with it detecting the malicious nodes, approximately more than 80%. The recall metric indicates that the alarms raised were only by malicious nodes, but not all malicious nodes were able to raise an alarm. And this is shown by the precision value. The selective forward attacks, the ratio and the block node, were expected to fail, detecting at least a 1/6 of the malicious nodes, as 4 nodes are edge nodes and do not forward any packets. Therefore, the attacks do not impact the activity of the compromised node. When the black hole attack is added to the selective forward attacks, the performance rates increase as the compromised nodes, including the edge nodes, lure neighboring nodes to forward their packets towards them and thus fail to forward it and makes it easier to detect. Now, the table on the right shows the results when the BLR models were evaluated with the unknown topology, where the sink was on the top. The precision, the MCC results were increased compared to the previous results. In the sink on top network topology, there are more relay nodes and the attacks can have higher impact. And there is only one edge node that is not affected by the malicious code. The current slide presents the results of the BLR when deployed in the IoT platform. The tables on the top row show the results of the selective forward attacks. In the forward duration, when the sink is in the middle, as the decision threshold increases by up to 1, the performance metrics are the same. When setting any threshold above 0.5, 92% of the alarms were raised by malicious node with a precision of 50%. The detection model correctly classified the node's behavior to binary malicious with 98% accuracy. The MCC value was 98%, essentially indicating that high detection model. As with the simulator results, it was expected that since 4 of the malicious nodes in the sink in the middle topology will not be detected, and when the BLR model evaluated to the unknown topology, the results were better. In the sink on top topology, when the decision threshold was set to 1, the absolute value, the recall, to 98%, with the cause that only 50% of the malicious nodes are detected. In the block node, BLR model's performance values depend on the decision threshold. The highest performance values are achieved when the decision threshold is 0.5. In both topologies, accuracy value is more than 95%, and the precision value is being at most 46%, indicates that not a lot of alarms were raised, failing to identify the malicious node, but correctly classifying the benign node. The selective forward and black hole attacks, BLR models, were evaluated at the IoT platform, had in certain cases better precision values compared to the simulator results. The black hole forward duration with threshold above 0.5 had a precision of 88% and 83% in the sink in the middle and sink on top topologies. The selective forward black hole block node models achieved the highest performance values when the decision threshold was set to 0.5. Overall, our results, both in the simulator and at the IoT platform, have shown that for each environment to be deployed, a customized BLR model should be created, and more than one performance measure should be used. The accuracy rate was even higher when few alarms were raised, since it takes into consideration the true negative alarms. The MCC, in our evaluation, said it normalizes the sizes of the benign and malicious activity present within the scenarios, and it avoids having high values when few alarms were raised. Future work in this area includes the experimentation with additional classification techniques, such as SVM, and using the same extended performance evaluation matrix. And that concludes my presentation. Thank you for listening.